observation of the Jovian system, Jupiter and its natural satellites, is of a prime interest for present. This archetypal planetary system constitutes in a way a miniature of the solar system and other unequivocal exosystems. The laboratory project presented in this movie focuses on Jupiter's internal dynamic, which is of a crucial interest as assets the whole planetary environment, including the giant magnetosphere, in which an incredible diversity of celestial bodies and potentially certain forms of life are enclosed. Unfortunately, despite being the nearest guest planet from Earth, the internal dynamic of Jupiter is poorly constrained from present observations. On the contrary, Jupiter's solar winds, visible on the present movie recorded by Voyager, have been observed for centuries and are well known of the large public. These large-scale dynamical jets are a privileged witness of a powerful internal dynamic inaccessible to direct measurement. Understand how the solar winds interact with planetary interior and how energy transferred through gas planets enveloped is a major challenge for a vast community of astrophysicians and planetologists. Furthermore, the self-organization of large-scale current flows is ubiquitous in nature and represents an essential research topic in fundamental fluid dynamics as well as in geophysics and planetary science. How these jets form and stabilize and how deep they extended within the planet are long-lived commanders in planetary science. Over the last decade, two models for explaining this relevant feature of planetary dynamics have been continuously challenged. A shallow layer model, where the fluid dynamics responsible for solar winds confines within the shallow troposphere, green weather layer, and a deep layer model, where the winds invade the entire molecular envelope, blue layer, that exists above the deeper dynamo region. To synthesize, in natural settings, solar winds develop for rapidly rotation flows in the presence of a strong boundary curvature due to spherical geometry. In particular, in physics, we argue that jets emerge in planetary flows when the Coriolis force, relative to the planetary rotation, dominate inertial forces, relative to the flow velocity, which in turn dominate the viscous effects, which dissipate energy in the system. All these ingredients are required to create a system in which strong solar winds spontaneously emerge. However, this can occur following both the deep layer and the shallow layer scenarios. We have developed a new laboratory experimental device that is capable of generating a strong Jupiter-like solar jets following the deep layer model. The working fluid is water containing in a 1.37 meter high by 1 meter diameter cylindrical tank. Once equilibrated at the rotation rate of 75 rotations per minute, the water's free surface takes the shape of a paraboloid, mimicking planetary curvature. Kinetic energy is supplied to the system for the bottom using a lattice of water injection points, namely a rotating jacuzzi. By the way, this experiment is called the Jovian jet in a jacuzzi. Here is the rotating device in the laboratory at Marseille. Using a top camera, corresponding the eye on the cartoon, fixed in the rotating frame, we record flow motion of the free parabolic surface. The guess is that we'll observe solar winds comparable to Jupiter's observable surface. We record from the top camera a 2-minute movie accelerated 6 times using black Indian ink as a flow tracer. Record initiates after 3000 rotation times when black ink is injected at 2 diametrically opposed locations on the free surface. The center of the frame corresponds to the center of the cylindrical tank, which is supposed to be the planetary pole. Ink is rapidly advected in the azimuthal direction by the solar jets, while radial transport is inhibited. Finally, a multiple jet system clearly appears. A new implementation of the experiment was to design a device emulating in a laboratory, a giant planet. Instead of a parabol light surface geometry, a plastic hemisphere constrained the flow to a spherical geometry. Except the change of geometry, the device remains the same than in the previous experiment. From a camera in the rotating frame, we record motions of the flow. The camera is comparable to a spacecraft mission which would be orbiting around the giant planet. We clearly see that the flow is dominated by zonal motions around the rotation axis and that large vortices develop. By rotating faster, we would probably observe stronger winds damping the small vortices, as in the case of Jupiter. Only the long-lived Jupiter Great Red Spot, this strong and stable vortex, remains to be explained by such laboratory experiment. That would be an interesting implementation for further experimentation.